So we'll be hearing from Yuan from University of North Texas on, well, ISM in a very different kind of system. So
Yes,
take it away.
Thank you. So when I was preparing for this talk, I wasn't really thinking about what T stands for in KITP. And then I heard all these theoretical talks yesterday, and I was like, okay, that makes sense. But we also had this discussion yesterday where we were trying to connect theories and observations. So I just hope that you don't mind me talking about both the theoretical side and the observational side. Okay, so like Christine said, I'll be talking about the multiphase filaments in the centers of galaxy clusters, and I'll be talking about their formation mechanism, their fate, and their kinematics. So a little bit of a background. Galaxy clusters are clusters of galaxies that are mostly held together gravitationally by the dark matter. And most of the baryons inside a galaxy cluster aren't within individual galaxies either. Instead, they exist sort of in between galaxies in the form of diffuse hot gas that often has a temperature above 10 to the 7th Kelvin, or 1 keV. And we call this diffuse hot gas the intracluster medium. We can see this intracluster medium in the X-ray because it's emitting X-ray photons via Bremsstrahlung radiation, so it is cooling. And we can estimate the cooling time, which is the time it takes for the gas to emit all of its thermal energy. And many of you probably have heard of the cooling flow problem in the centers of galaxy clusters. What is the cooling flow problem? Well, in the centers of relaxed galaxy clusters, the cooling time is usually only a few hundred million years, which is much shorter than the age of these systems. And that means these systems have the time to reach a steady state. And in a steady state, we expect gas to be cooling at rates of hundreds up to 1,000 solar masses per year, presumably into forming stars. And then the gas from the outer parts of the cluster should flow inward to replace the gas that has cooled at the same rate. And this pressure-driven inflow is the so-called cooling flow. Now, the cooling flow problem is that we don't think there is a cooling flow because we don't see a catastrophic cooling in the centers of galaxy clusters. And most people believe that the solution to the cooling flow problem is the feedback from supermassive black holes that pumps energy back into the system to offset the radiative cooling loss. So what I'm showing you here on the left-hand side is the central region of a galaxy cluster that's called the Perseus cluster. It's a nearby cluster, so we can see a lot of the details. And you can see these X-ray cavities or bubbles that are created by the feedback from the supermassive black hole. Now, even though the feedback from the supermassive black hole suppresses cooling, it does not completely shut off cooling. It only changes the level at which cooling is happening and the way that cooling is happening. So if we look at the same galaxy cluster in the H-alpha band, we see these really beautiful filamentary structures that extend out to tens of kiloparsecs. And that's here shown in red. H-alpha probes gas with temperature of about 10 to the 4th Kelvin. So technically it is warm or cool, depending on who you talk to. But sometimes I just loosely refer to it as the cold gas because it's much colder than the hot X-ray gas, which is shown in gray, by the way. And oftentimes there is indeed a cold component in these filaments as well that can be detected with ALMA and other radio telescopes. And just like cold molecular clouds everywhere else in the universe, these cold molecular clouds in these filaments in the centers of galaxy clusters are also forming stars. So what you're looking at here are actually a bunch of Hubble UV images of the central galaxies of some nearby galaxy clusters. And you can see these filamentary star-forming structures of all different shapes and sizes. And I'll come back to that later. Cold gas not only forms stars, it also fuels black holes. So what we've learned from the past decade or so is that black holes really don't seem to like hot gas. If hot gas is the only thing available to black holes, they just don't accrete at the rate we think they should be. But both data and theory suggest that when cooling becomes efficient, black hole accretion becomes efficient as well. And that's why it's so important for us to understand what's going on with the cold gas. Now, before we talk about the fate of the cold gas, we should first understand how it even gets there. In the past decade or so, there has been a lot of theoretical and numerical studies on the formation of multiphase gas, both in the center of clusters and in the CGM. And many of these papers are actually done by people here. If you think I'm missing anything, please let me know and I'll add that to the list. So what I'm showing here is just some figures from the paper by McCord et al. 2012. And Irina talked about her work yesterday, which is similar to this. And I would say the majority of these papers are focused on or are based on the idea that the cold gas forms out of the hot intercluster medium because of thermal instability. And I also did my thesis that's similar to this, but I like to call my simulations more realistic. So what I did is I set up a idealized galaxy cluster based on the Perseus cluster, and I put a black hole in the center, which sends out a pair of jets when it's being fed. And what we can see is that soon after the jets are turned on, the hot intercluster medium starts to cool into these cold clumps along the jet propagation direction. And what we think is happening is, is that the jets are pushing the low entropy gas from small radii with short cooling time to larger distances where the cooling time can become comparable to the local dynamical time there, and therefore allowing thermal instability to develop. If I zoom into that region and show you the whole distribution of the cooling time of the gas, you can see that the cooling fingers to develop out of the uplifted low entropy gas with short cooling time. So that idea makes a lot of sense. And I would say that most people within the cluster community, especially the theorists, think that multiphase filaments we see in cluster centers form out of local thermal instabilities, which are likely triggered by AGN feedback directly or by feedback-driven turbulence. However, there is a major problem with that model, and that is the model does not explain the existence of dust. The hot intercluster medium is dust-free because dust sputtering time is extremely short at high temperatures. And if all the cold filaments form out of the dust-free hot gas, the cold filaments should also be dust-free. However, observations tell us that they're all dusty. So how does the dust get there? We know dust is made in the winds of AGB stars. So I recently did this experiment where I basically put an AGB star in a wind tunnel simulation to see what happens to the wind coming out of an AGB star as the star moves through the hot background. I was hoping that some of the cold, dusty material could be preserved. Unfortunately, even though I do see some induced cooling in the tail of the AGB star, eventually the tail gets mixed back into the hot phase, and presumably all the dust grains are sputtered. So I can't solve this problem, at least not right now. I do think, though, there is an alternative solution, which is we just abandon this whole thermal instability idea And instead, we just directly launch multiphase outflows. And I want to advertise for this recent paper published by Yu Chu, who's the KIA fellow. And instead of putting in single phase hot jets like I did, Q put in multi-phase outflows from the black hole. And what we see is that there is a warm ionized component in the multi-phase outflow that can travel pretty far. And it cools as it travels to far distances. And because temperature never gets that high in this whole process, dust grains can be preserved. And I see this model as a very attractive alternative to the thermal instability idea. Now, regardless of how the cold gas gets there, we see it. So we want to know what it does, what happens to the cold gas. There's not a whole lot of surprise there. Like I said, cold gas forms stars and cold gas feeds the supermassive black hole. But if you put all these ingredients into a simulation, you actually see something interesting. So what we see is, as a result of the interplay between cooling, star formation, and black hole feeding, black hole feedback, the system goes through these long-term duty cycles. And I think that explains naturally the diversity of these star-forming structures that we see in nearby galaxy clusters, because on larger scales, these clusters don't look that different from each other, but they have very different levels of star formation in the center. And what I think is happening is really just us catching these clusters at different evolutionary stages of the feedback cycle. So, ta-da! So I thought my model was perfect, you know, apart from the dust problem. We solved the cooling problem, we solved everything. But of course, my model is not perfect. And I only realized how bad it is when I started looking at the kinematics of the multiphase filaments. So before I talk about the kinematics of the cold gas, let's first talk about the kinematics of the hot gas. We think that the hot intercluster medium is turbulent, just like gas everywhere else in the universe is turbulent. But it's actually not that easy to prove because of the limits of X-ray observations, which we briefly discussed yesterday. So the best evidence supporting the idea that the intercluster medium is turbulent comes from the Hitomi line broadening measurement. I think Irina briefly mentioned Hitomi yesterday. Hitomi was this lovely X-ray telescope that tragically died after it made one observation. And that one observation was looking at the central region of the Perseus cluster. That's the square. What Hitomi told us is that within this region, there is a line of sight velocity dispersion of about 100-something kilometers per second. And we think that that comes from turbulence. Now, because Hitomi doesn't really have good spatial resolution, this is pretty much all we know. Now, even though I was a theorist, I knew that X-ray telescopes usually don't have good resolution. If you want good resolution, you want to use optical telescopes. So here you're looking at the H alpha filaments again, observed with optical telescope. But instead of showing the intensity, now I'm showing you the line of sight velocity of the filaments. And usually when an observer publishes a paper with a map like this, they'll say, oh, look, the motions of the filaments appear random. But are we seeing turbulence or it's just random motion? Well, there are actually calculations that can help us figure that out. And so what I did last year is I calculated the velocity structure function of the filaments. So it's a very simple calculation. I basically look through the map, and for every pair of pixels, I record their separation and their velocity difference. And then I calculate the relation between the pair separation and the mean velocity difference at the separation. So that's the first order velocity structure function shown on the right-hand side. And the velocity structure function of the Perseus filaments is consistent with what we expect for a turbulent flow. Because on small scales, we see this beautiful power law that tells us big worlds have little worlds, which feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. And the velocity structure function turns over at about 10 kiloparsec, which is what you would infer as the driving scale of the turbulence. Now, this scale, 10 kiloparsec, happens to be the size of these bubbles that we see in the X-ray and also in radio. Are we seeing turbulence driven by these bubbles? Now, in case you're not convinced, I have also divided the filaments into inner filaments and outer filaments. And the inner filaments follow a structure function shown in red, and you see a more prominent bump at the 10 kiloparsec scale. Now, the outer filaments follow a structure function shown in green. You can see outer filaments don't seem to care about this characteristic scale. Instead, the power continues to rise towards larger distances. That makes a lot of sense because the outer filaments are not influenced by these inner bubbles.
3 minutes.
Okay. I do think that there's a hint of energy injection at scales around 20 kiloparsec, which happens to be the size of the outer bubble here. So it's possible that the outer filaments are following turbulence driven by a previous AGN outburst. And I think the case is more convincing for another galaxy cluster, Abell 2597. So the inner filaments review a driving scale at about 5 kiloparsec, which happens to be the size of the inner bubbles here. The outer filaments review a driving scale at about 20 kiloparsec, which is about the size of these outer bubbles. And I have also looked at Virgo, and unfortunately we don't have observations of the outer filaments here. And this was the first time I finally understood the observers and why they always wanted more data, because I want more data. But I looked at the central filaments in Virgo cluster, and I see the same thing. There's a beautiful power law on small scales. By the way, the thickness of the line here is the uncertainty of the measurement. And then there's a driving scale that you can infer that's about 1.5 kiloparsec. And that happens to be the size of this cute little jet there and the size of the inner bubble that's driven by the jet. So I think in all three clusters I've looked at, I find convincing evidence that there's turbulence, and the turbulence is driven by the feedback from supermassive black holes. Now, what does this analysis tell us about the coupling between the cold and hot phases? What do I mean by the coupling between cold and hot phases? If the cold gas is poorly coupled to the hot gas, then the cold clouds will behave more like apples. So when apples fall, this apple won't know what the other apples are doing. So the velocities would not be correlated. Now, if the cold clouds are better coupled to the hot phase, then they'll behave more like leaves. So they'll all float together, and you can even treat them as tracers of the wind. And I think that just the sheer fact that we see turbulence in the motions of cold gas tells us that even though the cold blobs are physically separated from each other, they all follow some large-scale coherent turbulent flow. And we're more convinced when we compare our optical analysis with the X-ray analysis. So like I said earlier, Hitomi doesn't really have good spatial resolution, so I can only put horizontal lines here for the Hitomi results. But you can still see that the Hitomi measurement for the inner region has an amplitude consistent with our measurement, and the Hitomi measurement for the outer region, which more or less covers the outer filaments, has an amplitude consistent with what we see for the optical filaments. And the more remarkable comparison comes from the comparison with Irina Shvablova's analysis based on Chandra observation. So what Irina does is she figures out the level of turbulence by looking at the surface brightness fluctuations that we see in using Chandra. And the turbulence that she can infer for the same region that covers the outer filaments is perfectly consistent with what we see based on the analysis of the optical data, at least within the range that X-ray observations can probe. So we think that this result tells us there is very good coupling between the cold and the hot phases in cluster centers. Unfortunately, that's not the case in my simulations. So now this gray line is the Perseus result, and this purple line is the structure function of my filaments in my simulated Perseus. And I was worried that maybe I was catching my cluster at a bad time, so these fainter lines are from other snapshots. You can see that my cluster consistently produces a much flatter structure function. And that, I think, is because my cold clouds behave more like apples. They move more or less ballistically. So you can have two clouds passing each other at high velocities, not caring about each other. And that gives you a boost of power on small scales, and therefore it flattens the structure function. I think it'll be very interesting to see what cosmic rays and magnetic fields will do, will change the picture. I don't have those simulations, so if you do, go ahead and try it. So, yeah, perfect. So to summarize, I hope that you would agree with me that cluster centers are excellent places to study multiphase gas, because we literally see all different phases in emission. And regarding the formation of multiphase filaments in cluster centers, we think that they may form out of the hot interclass medium, the result of thermal instability possibly triggered by AGN feedback. However, I can't explain why they're dusty. Alternatively, they may form out of multiphase outflows driven by supermassive black hole feedback. I think that more work needs to be done, even though a lot of work has already been done. And cold gas forms stars and feeds supermassive black hole in the centers of galaxy clusters, just like everywhere else in the universe. These cold filaments follow turbulence driven by supermassive black hole feedback and appear to be well coupled to the hot phase. And that is not seen in pure hydrodynamic simulations. Thank you.
Okay, thank you. We have time for a few questions. Clark.
Hi. First of all, fantastic work. This is all
Thank you.
Really cool. And I have a question about the thermal instability triggered by AGN jets. So I've read your papers very carefully. They were
Thank you.
when I was doing similar work with the fire simulations, and I still don't fully understand how to distinguish between thermal instability due to uplift and simply due to large density perturbations that result from like in place in the halo due to the AGN jets, because I mean that also will lower the cooling time. So I was wondering if you had any insight into that, because like I recently put out a paper analyzing similar questions in fire, and there's no winds at late times in fire. Cosmological substructure is still providing density perturbations that allow the hot gas to rapidly cool.
Yeah, so I agree that it's and I would to be honest with you and say my first thought when I was working on my thesis was that the cold clumps cool out of dense ICM. But we looked at we put in tracer particles and we looked at the evolution in the phase space, and we think that at least in our case, the gas that first cools is the gas that's being uplifted, and obviously, I can also go back to the movie. It is the uplifted gas. I don't know how I can go all the way back. So there's gas that's also uplifted but is warmer, and okay, here. So the gas that's heated up here won't cool. It is the also higher density gas that's uplifted that cools. And I would say without the jets, if you just have density perturbation, then you would develop instabilities in the denser regions. I would agree with you. Yeah.
Okay, thank you.
Thank you.
Okay, Todd?
Hi, thank you. You mentioned that the hot cluster gas has no dust, and you were talking about this dust problem. But the argument you offered, which is strong, is the physical argument that the dust should rapidly sputter. But I was wondering if you could comment on the empirical case. Do we know that the hot intercluster gas is dust-free empirically?
Yes. And
what are those constraints? Thank you.
Well, so okay, I'm not a real observer, unfortunately. I know there is very strong observational evidence telling us that the hot phase is dust-free. Okay. And the best person to talk to would be Megan Donahue, and she explained to me once, and I don't fully get it, but it's some lines that you would expect that are missing. So if there is dust, you would expect some lines, and you don't see those lines. That's my understanding of it, but okay. I'm not familiar with observations, so that's all I can say. But there's convincing evidence that the hot gas is indeed dust-free. Yeah.
Okay, we have time for one last question. Pratik?
Thanks, Yuan. That was a very nice talk. So actually, we have done a lot of these thermal instability type simulations, and recently we have done these cloud crushing simulations. And one thing that we realize is that these global simulations of the kind that we have done, and you have also done, really do not have the kind of resolution where we can actually get this momentum transfer between the hot and cold phases very, very faithfully, right? So even if you resolve the cloud by tens of grid cells, which is quite difficult in our simulations, even then the momentum the dense clouds move like bullets. They don't couple and become like the leaves blown by the hot wind. So that's one point that I wanted to make. And I have actually a lot of questions, but we can actually talk in one of those rooms.
Yes, I agree. I was trying to emphasize on physical processes beyond pure hydro, but I totally agree with you that just the resolution itself can also possibly make a difference. And I think the next talk by Evan will probably touch on that.
Okay. Well, great discussion, and I'm sure it will continue. So thank you, Yuan.